Good afternoon, everyone. My name is Tony Roskilly. I'm Professor of Energy Systems at Durham University, and I lead the EPSRC Network Plus on hydrogen-fueled transportation. This webinar is organized by Network H2, and it's part of a series of webinars looking at different aspects of hydrogen research that's related to the transport sector. This week, we welcome two speakers who will be presenting their findings of two projects that were funded by the network, which were investigating the techno-economic feasibility of hydrogen fuel transport and the optimization of hydrogen refueling locations for road freight. Our first speaker is Dr. Ramin Raeesi. He is a senior lecturer in the Management Science Department and a member of the Center for Logistics and Heuristic Optimization at Kent Business School. He's also a visiting researcher at the Center for Transport and Logistics at Lancaster University Management School and a member of the Future Energy Group at the University of Kent. Ramin received his PhD in Management Science from Lancaster University Management School, where he won the Kingsman Prize 2019 for the best doctoral dissertation. And prior to joining Kent, he was a postdoctoral research fellow in operational research at Brunel University, working on a Europe Horizon 2020 project on the development of a green and sustainable ecosystem for the EU port of the future. So Ramin, over to you.
Thank you for the introduction, Tony. Hello, everyone, and welcome to this presentation. I am presenting today on behalf of the team of investigators from 4 universities who worked on this project, a techno-economic feasibility study of hydrogen-fueled freight transportation. I will start with a brief project overview around our motivation behind the project, its objectives, work packages, demand, production, storage, and transportation scenarios considered, the modeling tool that was developed as part of this project, and some findings and outcomes and key insights, including concluding remarks and the potential next steps to take the project to the next level. So this project, as I said, was called Techno-economic feasibility study of hydrogen-fueled freight transportation. It started around this time last year, 15th of May 2021, and it was completed 14th of February after 9 months. The funder of the project was EPSRC through Network H2, which is led by Tony, and we at the Center for Logistics and Heuristic Optimization at Kent Business School were leading the project. The project team was composed of 4 investigators from Heriot-Watt University, myself, Cranfield University, and University of Exeter. And it was also supported by a team of research assistants and advisors, including Dr. Laura Marcialini, Krista, who is presenting after me today, Pega from Cranfield University, and Shima from the University of Kent. So I'll start with a little bit of background and motivation for carrying out such research. So for one thing, freight transportation accounts for more than 40% of transport-related emissions, and 65% of all of this is just due to road freight transportation only, which is a really large figure. With 1990 and 2010, the heavy good vehicles emissions increased by around 36%, and they are projected to grow to 40% by 2030. So shifting from fossil fuels to clean alternative fuel options such as hydrogen is an essential step in decarbonizing road freight transportation sector, which is having a lion's share in the total emissions from the overall transport sector. But why hydrogen? And why not the other net zero options that we are all aware of? There are a couple of reasons to go for hydrogen. For one thing, this is an energy carrier that is approximately 2.5 times more efficient than gasoline. It can be produced from conventional primary energy sources, such as natural gas, coal, petroleum, as well as renewable energies like solar, wind energy, tidal energy. And because of that, it contributes to the hot topic of energy security that we are facing today as well. So it is not just about net zero, but it is also about energy security. So with moving towards hydrogen, it can be independent from the current situation that is happening in the world as well. When we compare with other net zero options, such as electric commercial vehicles, hydrogen-powered trucks offer multiple competitive advantages indeed, particularly in long-haul distribution. These pertain to their larger driving range, their much faster refueling time. We know that refueling time and recharging time is an issue, for example, when we are talking about electric vehicles, and improve payload efficiency. So as much as, let's say, the electric commercial vehicles are favored for last mile delivery, and in urban areas, they are not really applicable to long haul transportation. And that's where hydrogen trucks play a very important role in the future of road freight transportation. Okay, what is the main challenge that we were trying to address as part of this research? For one thing, the most clear challenge in the face of a hydrogen economy for road freight transportation is the lack of the infrastructure that is required for producing, storing, transporting, and distributing hydrogen. We know that designing an economically viable and competitive hydrogen supply chain to meet the end user demand is not easy. And the ultimate price of hydrogen at pump really relies on the optimal determination of production, storage, and storage facilities, their location, their technology, their capacity and size, the required capital investment and operational costs that they involve, and then ultimately connecting them using cost-effective, sufficient, and appropriate transport links. So this is, at the strategic level, the key challenge in the face of the hydrogen economy to fuel the road freight of the future. A gap in the existing hydrogen supply chain network design knowledge. So from this point on, I am using HSC to refer to hydrogen supply chain. There is actually good literature on hydrogen supply chain network design. And these are mostly tools that are designed for optimal deployment of hydrogen infrastructure and a strategic hydrogen supply chain design through especially explicit optimization models that consider the entire hydrogen supply chain and run at a national or regional level. These models integrate multiple components of hydrogen supply chain corresponding to production, storage, transportation, and all of these are integrated within a single optimization framework. And the output of the optimization process is usually the number and location of the required facilities with their adopted technology and size, as well as the transportation infrastructure needed, while minimizing the capital and operating costs of the HSC. One thing about most of these models is that they are mostly based on centralized production, hydrogen production. So these are rather large hydrogen production sites, which are off-site from where hydrogen is needed. And most of the existing models that we have in the literature actually are based on these centralized modeling tools. And it is interesting to see that, ironically, the largest proportion of hydrogen supply chain cost is dominated by hydrogen storage, transport, and distribution, rather than the hydrogen production. This is actually an explicit finding from almost all of these studies that have used one or another sort of these tools. So when you produce hydrogen centrally, and then you need to take it to where it is needed, let's say to the final point of delivery at a refueling station, you have to transport the produced hydrogen into a bulk storage site. From that bulk storage site, you have to again transport it point of need. And all of this, the transportation and the storage, is really costly in the overall hydrogen supply chain costs and figures. And this is something that is a gap in the existing hydrogen supply chain network knowledge. There are studies that are specifically looking at on-site hydrogen production. These are, again, focusing only on on-site small scale hydrogen production rather than seeing the entire picture. So where would it be best to produce hydrogen centrally, and where would it be best to produce hydrogen and use it on site? So the literature is either to the centralized side, or to the on-site side. There is no research that can link the two paradigms. So tools for incorporating both on-site and centralized production decisions into an integrated modeling framework are largely missing, and this was one of the first things that we observed as we started reviewing the pertinent literature in this area of research that we were carrying out. So the main project objectives and contributions, we were aiming to build a techno-economic model for understanding the economies of hydrogen utilization for land-based freight transport in Great Britain. As I just mentioned, we wanted to develop a new hydrogen supply chain network design tool that integrates decisions on centralized and on-site hydrogen production simultaneously. We also wanted to see where the potential hydrogen supply chain refueling stations for major heavy good vehicle routes should be. So the identification of the location and size of refueling stations was part of the work as well. And we also intended to include all state-of-the-art blue and green hydrogen production and storage technologies, and develop key insights on the economies of establishing a hydrogen supply chain to support the route of hydrogen HGVs. The entire project was delivered over 3 work packages. In work package 1, we focused on model development and demand scenario generation. So as part of this work package, we tried to understand the potential demand for hydrogen from the future hydrogen-powered truck fleet. We wanted to see how this demand is potentially distributed, what would be the potential location of hydrogen refueling stations, what would be the size of each refueling station in the network that we see in a strategic level. Of course, there are much further details to refueling stations, and I know Athena project, which will be presented after this, paid a lot more attention to this aspect of the work. Then following this work package, we also developed supply scenarios for hydrogen production, hydrogen storage, and transportation. And finally, over WP3, all of these scenarios that were generated were exercised against the model that was developed as part of WP1, and the work package was focused on techno-economic scenarios analysis. So a little bit about different aspects of the work, starting with demand modeling. We started with collecting data pertaining to current road freight energy consumption, as well as existing refueling stations servicing the current diesel HDV fleet. We used data from 2019 mainly to bypass the effect of COVID, and using the data, we realized that the demand for diesel fuel for HGVs in the UK during 2019 was over 6 million tons. This is translated to over 5 billion liters of diesel and a total annual energy demand of over 49 billion kilowatt hour, which is huge. So if we assume the same figures are going to remain as they are and taken to year 2050, when the net zero ambitions of the government have to be met, and assuming that the entire HGV fleet is converted to hydrogen, then this is how much hydrogen that we need, 49 billion kilowatt hour a year. We also collected data on existing refueling facilities. These consisted of over 1,700 records of warehouse facilities, around 300 service stations, and over 50 ports, and all of them were consolidated and combined to create a final set of 539 records of candidate facilities for hydrogen refueling stations. In terms of the size and the capacity of these refueling stations, we used data where it was available. When we had incomplete information, we conjectured from for example, the size of the warehouse, what the potential size of the refueling station shall be. So this is a representation of where refueling stations are located within Great Britain, and the size of each circle here shows the capacity of this particular refueling station. In terms of hydrogen production technologies, as I said, we tried to include our state-of-the-art blue and green hydrogen production technologies. We considered three blue hydrogen production technologies corresponding to steam methane reformer with carbon capture, usage, and storage, autothermal reformer with carbon capture and storage, autothermal reformer with gas-heated reformer with carbon capture, usage, and storage. And in terms of green hydrogen production, we considered alkaline electrolysis, proton exchange membranes electrolysis, and solid oxide electrolysis. So some of these technologies like SOE and ATR plus GHR are still not operationalized, but based on the data we use from BASE, they are expected to be cost effective for hydrogen production by 2030. So we still included them in the study because we had a look ahead analysis of the future hydrogen economy in this study. We collected all the data regarding the different plant outputs, the minimum production capacity of these outputs for them to be operationalized, their maximum production capacity per day, capital cost involved over different years as was reported in BASE report, and also the unit production cost. So all of these were collected. We also collected some data on existing or planned hydrogen production sites in Great Britain. We divided the entire region of GB into 34 different grid structures. And within each grid, we could identify whether there is any existing or planned hydrogen production site. In terms of hydrogen storage technologies, we considered both underground and overground hydrogen storage technologies. As long as underground storage is considered, we considered pipe storage, lime rock cavern, and salt caverns. And for overground, we consider compressed hydrogen gas tank at 700 MPa. And similar to the case of hydrogen production, we collected all required data on capital cost and unit storage cost. Again, for hydrogen storage, we tried to identify existing sites for underground hydrogen storage, and we mapped them to the grid structure that we developed. For transporting hydrogen from where it is produced to where it is stored and then to where it is delivered, we considered only one mode of transportation, and that was tube trailers, which carries hydrogen in its gaseous format, CH2. So the reason why we excluded other means of transportation between different supply chain entities, like, for example, let's say pipeline network, was two things. For one thing, for the considered case of let's say road freight refueling, tube trailer makes the best sense based on our analysis of the existing knowledge in the literature. And on top of that, given the duration of the project and the access to the data, it was very difficult to include the data on pipeline network in the country. So we had to exclude that from the consideration, and we only relied on tube trailers. We developed a modeling tool which intakes all of this data and in the background runs two different mathematical optimization models to understand which refueling stations to open, which production sites of what size and what technology shall be open in which grids, and how is hydrogen transported, at which sites, which hydrogen refueling station sites it would be best to produce hydrogen on site rather than getting it from centralized hydrogen production, and so on and so forth. So these two tools, this set covering optimization model to identify refueling stations, sizes, and locations, and also the hydrogen supply chain network design model, where at the heart of each stage, which take all the data that I just referred to and output the optimal design of the supply chain based on both centralized and on-site hydrogen production. These two slides are a little bit technicality on the model, so I tend to skip them as I am also conscious about time. So the techno-economic scenarios that we considered to exercise against these two-stage modeling tool that was developed were 11 different scenarios. We started with a baseline scenario SC0, and in this scenario, we left the model to decide whether on-site or centralized the hydrogen production should be established, so the model can freely decide. We assume the entire HGV fleet in the UK is converted into hydrogen. We allow the model to decide whether to go with blue or green hydrogen. And we let the model to freely decide whether existing identified sites for hydrogen be used as part of the hydrogen supply chain for road freight or not. And we planned for the year 2050. So all the cost figures used were for this year. Now, the other scenarios change one or several aspects in the baseline scenario. So for example, in scenario 5, which opposes what we developed as part of this study to what is existing in the literature, is that we just rely on centralized production and ignore on-site hydrogen production and see what happens and how much cost are we saving with the developed tool. Or for example, here we turned off the blue hydrogen production option, so green hydrogen production only, to see what does it cost to just produce hydrogen, green hydrogen for road freight, and so on and so forth. So all these configurations were exercised against the modeling tool. I skipped this one, so this is just representing the sites that were opened and those that are potentially ready for passing to the next stage for on-site or centralized hydrogen production. So as you can see, this is the total sites that we identified as candidate list. These are those that have not been opened, and blue and green ones are opened ones. Blue ones show the potential for on-site blue hydrogen, small-scale blue hydrogen production, and green ones show on-site small-scale green hydrogen production opportunities. But this is not yet decided, and it is passed to the second stage, which decides whether to establish on-site or go with centralized hydrogen production. After optimizing the baseline scenario, we get something like this. Of course, there are a lot of details to the output, but there is just so much that we can represent in a figure. So for example, just if I want to very briefly mention what is happening here, these are the sites that the blue points are the hydrogen refueling sites that are supplying their own needed hydrogen based on-site small-scale blue hydrogen production. The green ones are, again, independent and on-site hydrogen production based on green technologies. And then these squares, these blue squares, show centralized hydrogen production, and you can see the transport links. So for example, if this is a centralized hydrogen production in this grid, all the demand, it satisfies parts of the demand in this grid, and also transports to this one here, grid 10. Or for example, this one satisfies parts of its own demand and also transports to other grids. So that is what we ultimately get, and we can design the entire supply chain to address what is demanded by the fleet. Just a couple of interesting figures and what we have achieved with the modeling tool that was developed as part of this. So as I mentioned, in baseline scenario, we allow decisions to be centralized or on-site freely. But in scenario 5, we force the model to just go with centralized, what is existing in the literature. We can see how much we are saving in total capital costs with this modeling tool. So we are coming down from over 4.5 billion pounds to just 3.5 billion pounds in capital investment. And the total daily cost of the hydrogen supply chain is also significantly dropped. We can see also, as I mentioned earlier, over 70% of the total cost in centralized, let's say, scenario is just taken up by capital investment required for storage facilities. And this shows the opportunity for going on-site where possible. And this shows how much goes to from the total capital cost required to production, to storage, and to transportation. So very quickly, some interesting insights from our optimization analysis. So we noticed that with the total capital investment of 3.5 billion, the required hydrogen supply chain network to fuel the road freight of the future can be established. I personally believe that is not super huge, but what makes the situation very difficult is the other side of the picture, which is converting the total hydrogen, the heavy duty fleet into hydrogen power HDVs. This requires around 400 billion investment commitment from freight forwarders. And this figure is then very huge and requires a lot of commitment from freight forwarders and a lot of funding support from the government as well. This is in case we want to convert the 100% of the fleet to hydrogen-powered trucks. But if you just want to convert 20% by the year 2050, we need less than £1 billion in capital investment for developing the infrastructure needed, but still £80 billion for enticing the companies to invest and convert 20% of their fleet. So still this figure is huge. And I think one of the findings of this study was that instead of focusing too much on the infrastructure side and forgetting about the demand side, this partially addresses the chicken and egg situation, which we are always facing, whether we should first develop the infrastructure or first create the demand. I think in the case of hydrogen, definitely the infrastructure should proceed. In the baseline scenario, the 72% of demanded hydrogen is supplied through on-site hydrogen. So we should be more serious with on-site hydrogen, and where possible, this should be established because it reduces lots of costs corresponding to storage and transportation. We find that most of on-site hydrogen production are based on a small blue hydrogen production technologies though. So this is not the best thing, but this is because green hydrogen production is still very expensive. If we insist on going fully green in hydrogen production for road freight, we increase capital costs by 22%, which is not huge, but then daily cost increases so much it becomes almost double. These are other things about the best preferred kind of hydrogen production technology and storage technology, which I skipped. Just a very brief indication of potential next steps. I think it is very important to carry out a next study on multimodal shared hydrogen refueling infrastructure, because at the end of the day, all modes of transportation will use the, let's say, hydrogen refueling stations at certain points, like ports. So ports are key in here. they can satisfy part of the maritime need as well as the road need. And most of our HGV routes start from the port. So this is a very interesting and important next stage project. Other things like inclusion of pipeline that we were unable to consider as part of this study would be interesting to explore further based on the existing infrastructure in the country. I think with that, I can stop my presentation and wait for questions. Thank you very much.